In this section, we will explain about microservices architecture and see its guidelines and structure. In this video, we will learn about the basic theory of microservices and look at some pitfalls to be aware of. Microservices is definitely cool, but there are other ways to go. On-premise platforms may require more traditional installation methods, pushing for Java or IIS service. Startups who want to move fast may go serverless, also called cloud native, gaining speed by adopting a specific platform while paying for it in vendor lock-in. Using Dockerized microservices has an initial overhead but is much cheaper than serverless when you have large traffic volumes. Many companies say they want to be cloud agnostic and to have the option to switch infrastructure either in order to save costs or to be able to deploy on-premise later. It is important to understand that there is a cost for this abstraction and that there will be additional costs for switching since some of the facilities you will inevitably use are specific. Object services like S3 have no standard API across clouds and are irreplaceable for saving files and media. Database and cache services usually do have a standard interface like Redis and Postgres, but may introduce specialized authentication systems. Managed Kubernetes solutions have specific cloud integrations for authentication, logging, and network system. So you can see what I mean. The actual choice whether or not you choose to be tied or free of your own cloud vendor. It is more like how much would you pay to be less bound to it. If easy switching is not inherent to your project needs, you should consider using cloud infra in order to reduce investment in abstraction and DevOps and shorten the time to market. Services are the base of this architecture, and they are defined as self-contained units which own their own data, exposing it to others only via APIs. Each platform has its own lightweight authentication validation and enforces permissions in its own domain. A service has a well-defined API, which means that it can be replaced by another implementation of this API. The last service property is less clear-cut. Services are defined to have a single responsibility, which requires additional investigation in order to define what a responsibility actually is and how wide it can become. Let's have a look at the single responsibility guideline. We should understand that if we take this too literally, we will end up with nano services. Each one will have one API and an extremely interconnected tangle of second-hand calls to internal APIs. Encapsulating small but complete logical units is what we should be after. Such a logical unit can have several responsibilities as long as the responsibilities are coupled in a way that make them hard to separate and that makes sense to us. Another emergent property is that since each service communicates over standard protocols, it is free to choose its own implementation and tech stack. This can get messy since more technologies mean more knowledge, more implementations of common infrastructure like clients, reading configuration, and data access facilitation code. In my opinion, you should pick one good language to begin with and add others out of necessity, since lift and shifting legacy code can necessitate other languages, or for special needs like dealing with CPU-intensive operation or doing data science. Like most architectural decisions, you should plan and control to avoid making a mess.